Let's talk about circuits and Ohm's law. If you watch the resistance PowerPoint, we did talk about Ohm's law a little bit, which is that relationship that has to do with resistance, potential difference, and the current. So who was Ohm? He was a dashing young man. Here's George Ohm. He was a German physicist who determined that current that flows through a wire is proportional to its cross-sectional area and inversely proportional to its length. He was able to define that relationship between voltage, current, and resistance. We know this as Ohm's law. Again, these are things that we did discuss in a previous video about resistance. If you haven't watched that one yet, I'd watch that one first. So what are these relationships? Ohm determined that how much current a particular circuit carries through depends on the potential difference. So the amount of charge that flows through your circuit depends on how much potential you give those charges. That should make sense. The more potential you give them, the faster they'll flow, which means you'll have more current. The other thing that this depends on is the resistance. Now remember, resistance is thought of as electrical friction. So resistance is going to slow those charges down. So how much current travels through will also depend on the resistance. This is an inverse relationship. So the more resistance you have, the more things that are going to slow those charges down, the less current you'll have traveling through there. Right? So here's our relationships. Current, I, is directly proportional to the potential difference V. Resistance is inversely proportional. So here you see that. Current is proportional to 1 over R. There's your inverse relationship. Ohm was the one who determined these relationships, and we know this as Ohm's law. So Ohm's law, remember, is this relationship, R equals V over I. Again, I like to remember this as V equals IR, but that's just a personal preference, right? You could also solve it for I and remember it as I equals V over R. These all are the same relationship, same equation, solved for a different variable. Your reference table gives you that equation on the left, R equals V over I. One thing to remember about Ohm's law here, this is not a general law of electricity, right? It is called Ohm's law, but it's not a law that holds true for everything. It holds true for metallic conductors when they are held at constant temperatures. That is your key. So if you have something that's not a metallic conductor, it probably is not going to obey Ohm's law. If you have something that the temperature is changing, it will also not obey Ohm's law. So let's look at a simple circuit, right? Here you see a schematic diagram of a circuit. Over on the left-hand side where you see all of those little horizontal lines, that represents your battery. Remember, the little short line is the negative side of the battery. The long short line is the positive side. So the way my battery is oriented, the negative side is up and the positive side is down. So electrons are going to leave the negative side, go up. They'll travel through the ammeter, that big circle with the A. Then they'll travel down through that squiggly line, which is the resistor, and they'll go back to the battery. On each end, you see a circle with a V in it. V total, that is a voltmeter that's going to measure the potential difference of the battery. On the other side, you see a voltmeter around the resistor, V1. That will measure the potential of the resistor. Right? Really, that's going to measure the potential drop, how much energy the resistor is taking away from those electrons. So one thing to notice here, the ammeter is connected in series, right? It's connected along the same path. So all of the electrons have to go through that ammeter. It's going to measure the current flowing through the circuit. To measure the voltage, we placed voltmeters around the battery on the left and around the resistor on the right. These are added in what we refer to as parallel. So that means they kind of get clipped around each of those devices on their own. In the activity that we started in class, where you were using the PhET simulation, you were asked to build parallel circuits. So you should have a little bit of an understanding of a parallel circuit and how things get added in parallel. But we'll talk more about that. Notice in this circuit, both the source, the battery, and the drop, the resistor, will have the same potential difference. So notice two words I've used there. Potential source, which comes from the battery, that's giving those electrons energy, and potential drop, which comes from the resistor. That takes the energy away. In this circuit, they have to be equal because if you, again, remember that simulation, if those electrons go back to the battery with extra energy left over, that's when you get a short circuit. And in that simulation, that's when you created a fire. We don't want that. So let's just look at some sample data. Here's my same circuit. I'm going to give you some data. So here's data that was collected. And this is something that we would do when we do Ohm's law, build a circuit, collect some data. So what you'll see here are three columns. You have V total, which is the potential difference of the battery. That is something that you are controlling. So you can determine how much potential you give those electrons. Right? So that's my control. The other two columns, V1 is my potential drop. That's the reading on voltmeter 1, the reading of how much potential is being taken away from the electrons. And then you also see there the current. Right? That is something that is going to depend on how much voltage you add. So you could sit here, you could analyze these numbers, and hopefully you could come up with the relationship, and you'll see that as the total voltage increases, goes from 0 to 16, my total current also increases. It goes from 0 to 8. However, we don't like to analyze things numerically. So what we're going to do is actually draw a graph. Okay, so here's our graph. When we are looking at graphing circuits, typically you'll be asked to graph potential difference voltage versus the current. Right? So voltage will be on the Y, current will be on the X. And here's what we get. So you'll see there's a nice direct relationship when we add this best fit line. If you were to calculate the slope of this graph, something that you should try, maybe pause the video, see if you can calculate the slope. Remember, slope is change in Y over change in X. So we're looking at change in voltage over the change in current. If I pick two values here, right, I'm going to use the point 12 volts, 6 amps, and I'm also going to use 0, 0 since it does go through 0. I get 2 volts per amp. Now, do you remember what a volt per amp simplifies to? What unit? That is ohms. So the slope of a potential difference versus current graph gives you the resistance of your circuit. Very important. So if you were asked for the physical significance of the slope of this graph, you would say resistance. Okay. Things to take note of here. Since the slope of this graph is a straight line, that means the slope is constant. We know that the slope represents the resistance, so the resistance of that material that the data was collected on is constant. That means that this material obeys Ohm's law. Here's your key. When you get a graph of voltage, potential difference, versus the current, and you get a nice, straight, direct relationship, that obeys Ohm's law. If instead you were to get a curve, that is a material that does not obey Ohm's law. And that would mean the slope is not constant. So that would mean the resistance is not constant. Those are things where the resistance changes over time. Right? So the key to know, if it's a straight line, it does obey Ohm's law. If it's a curve, it does not obey Ohm's law. And those are things where the energy is going to change. So things that heat up will not obey Ohm's law. Things that make a noise typically won't obey Ohm's law. Things that light may not obey Ohm's law. Right? You have that transformation of energy turning into something else. This last slide is just kind of a list of things that we'll need for this unit, right? And so you'll see different quantities that we've talked about: potential difference, current, resistance, and then powers at the bottom, right? We did talk about power when we talked about energy, but we will talk more about power in circuits. Right? You see the symbols for each of them, the equations that are all on your reference table, and then the derived units and the practical units or the simplified units for each of them. Might be something to, take a picture of or copy down in your notes, but again, all of this is on your reference